Very close. And all right, so that's put away. Okay, more better. Much better, much better. All right, so let's see who we have on here so far. Rebecca, Pauline, Pedro, Andrew, Gabriel, and there's a few other people that aren't here yet, but welcome. And how's everybody doing in the midst of all of our shelter in place? Hope that you enjoyed some kind of rest during spring break. And let's just go ahead through I'll tell you a little bit. My spring break, well, actually before spring break, been on the treadmill for about half a month and only lost half a pound. There's no justice in this. Those are really good workouts, and only lost half a pound. But I think if I want to look at the glass being half full versus half empty, at least I didn't gain weight for all of the more time that I've been sitting down and eating more, I guess. So the good thing is, yes, I'm not gaining weight. I'm actually losing, but not losing at the rate that I was hoping for. So that being said, Pauline, how was your week?
Sorry, I muted myself. Anyways, well, my week has been really strange. I was running and now I had to stop running just so I could be sheltered in place. But all in all, everything's good. I mean, I can't complain. I really can't complain. I mean, New York has been really hit, and I have a few friends there, so I am praying for them. But
Yeah.
all in all, I'm very grateful that we're still healthy.
That's a good place to be, and thank goodness for all of our health being where it is, and pray for our friends and relatives that are not doing quite as well. Rebecca, how's your week been?
It's been fine. No, not much has been going on. Been trying to find stuff to fill the void of time I have now.
Yes.
Other than that, I've been okay. Going a little bit stir crazy, but trying to deal with it.
Yeah, no, the cabin fever is kind of an interesting thing. My wife and I, at one point in time, almost came to fisticuffs, and then we realized, no, it's cabin fever. It's this extra time of face to face that we're unaccustomed to, and we readjusted, so that worked out okay. Pedro, how's your week been?
It's been fine. Nothing really changed since I usually don't really go anywhere.
Mm-hmm. Okay. All right.
But overall, it's been good.
Good. Hopefully, interesting with a lot of my relatives and friends. Spring break was also the time for spring cleaning, so they've been sending text pictures back and forth. Oh wow, I can see the bottom of my closet now. What a remarkable thing! It's like, oh, okay, that's great. So some positive things did come about for this extra time. I see Andrew. Andrew, how's your week been?
It's been pretty good. Just trying to keep busy and stuff, and been barbecuing a lot at the house here and everything like that, and
Hey, barbecue.
Yeah. Kyle's here with me.
Yeah. Oh, excellent. All right. So I'll make sure we jot that down on the roll sheet. And I see Gabriel, you were on, you were off, and now you're back on. Tell us how your week has been. You have to unmute your microphone, pal. Gabriel, have you figured that one out yet? Maybe you haven't figured that one out yet. That's okay. So I've got Pedro, I've got Andrew, I've got Kyle, Pauline, Rebecca, 2, 3, 4, 5, 2, 3, 4, 5, 6, and Roscoe. Okay. Hey, yeah, Gabriel, your mic is unmuted now. Tell us how your week has been.
A lot of cleaning. A lot of cleaning. I'm a painter now. A lot of painting.
Oh, okay. So you're doing artistic masterpieces like the Mona Lisa type painting, right?
Oh no! I wish it was something like that. It's more of remodeling the house, painting the walls, cleaning everything up, throwing all the old stuff out, and pretty much just cleaning, relaxing.
All right. Well, that's good positive effort. So anyway, we find ourselves now in week 10, and we have a whole lot of stuff to do that wanted to have a chance to chat with you all about. So before we parted company, you were given a pack of extra parts, and I wanted to go through specifically these parts with you, and then in particular, one part in particular is the onboard potentiometer, and I'll talk more about this in greater detail. So what would be handy is if you could grab your bag of parts and your breadboard and some jumper wires, and if you have your multimeter handy, be sure to have that out, and we'll go through and do some lab lessons with you, and then we'll do some other lessons that I've planned for us. So if you can go and grab those parts, be sure to have your calculator as well, something to take notes with. We shall begin very, very shortly. The session is recording, so I will from time to time ask you to turn on your cameras because you're going to need to show me some things on the screen. So while some of our friends are still gathering their things, can you turn on the webcam on your computers so we can just do a video check? So we'll start with, hey, all right, there's Pedro. Hey, there's Andrew, fantastic. Kyle's in the background somewhere. Yeah, there's Rebecca. Yay, Rebecca. There's, all right, there's Pauline. Okay, Gabe, you get your camera on. Gabe, he's still working on technology.
I'm still trying to figure it out. Okay, there you go.
There you are. Okay, all right, fantastic. So this is great. What I wanted to show you, and I'll flip my video to go from my cam to my dot cam. And so here's my dot cam, and the particular part of interest is this little guy right here. Let me move this out of the way and bring this up close to the camera. And what it is that you see about this particular guy is it has 3 pins on the underside, like so, and it has a screw at the end, and that is where you would insert the little white screwdriver. It might be black, I don't know what color. I think most of them that I had distributed were white. And this goes into the slot and allows you to turn it. So physically what happens with this potentiometer is this. This is a miniature version of the potentiometer that you were given previously. So let me make some notes here for you. And first of all, let's state again that we have a potentiometer. And can you all see my writing fairly clearly?
Yes.
Try not to bleed too much. Okay, so potentiometer is a 3-pin variable resistor. The one that you had received last time was a design that's similar to this. Here's 1 pin, here's a center pin, and here's a 3rd pin. And what happens between the outside pins is a resistive element. It's kind of like this. It's a resistive element and attaches between pin 1 and pin 3. An interesting thing about pin 2 has what is known as, comes up here, big ball, and it has something like shaped like an arrowhead, and we call that a wiper. The resistor that you have, and it's turned by a big knob, the potentiometer that you have in your kit, this particular guy here, same principle. You still have a pin 1, you still have a pin 3 way out here, and you have a pin 2. Oops, pin 2. And this comes up, and it has wires, resistive element, and then it comes down here. And it turns out that the wiper, as we rotate this screw terminal, the wiper will move from left to right. The wiper will move from left to right on a track, like so. And so this wiper will move from one end of the winding to the other end of the winding, and therefore the resistance will change. So it turns out that the potentiometer that you all were given was between terminals 1 and terminals 3, a 500 ohm potentiometer, meaning that the maximum amount of ohms that we're going to see. Oh, 2 people in the waiting room here. Hold on. Let me get them in. Waiting room. Hello. And come up here. Okay, Mr. Lau. Yeah, turn on your microphone and turn on your camera so we can see you and you can join us, okay? Cool. I'll keep an eye on the screen as other people come on. All right. So as I was saying, between pin 1 and pin 3, you're going to have a maximum of 500 ohms. That amount of ohms will not change no matter what we do with the screw terminal, no matter where this wiper goes within this particular box, that's this enclosure. And it doesn't matter really whether we do our orientation with the screw terminal on the left and call this pin 1, 2, 3, or we turn this around, have our screw terminal on the right, and we call this pin 1, 2, 3. The important thing is between your outside pins, the amount of ohms will never change no matter how we adjust that screw terminal. So I will demonstrate this by simply taking our ohm meter and go ahead. I'm going to attach, oops, come back here, alligator here, and alligator here to my outside pins, and just set that down for a moment. Turn on my multimeter to ohms and adjust this so you can see this. And I can use this little screwdriver, or if you find that a little too small, then something else of a larger variety that you feel more comfortable in using might be the ticket. So I'm going to come up here, hold this potentiometer so I can get a good view of that screw terminal. And I'm going to stick my screwdriver into the shaft and start turning. And I'm turning, and I'm turning, and I'm turning. And it'll turn so far, then you'll feel that it won't go any further. Don't go past that point. You'll break it. You'll break the insides. So once it gives you some resistance, stop. Now start turning in the other direction. It's what we call a 10 to 15 turn pot. It'll take 10 to 15 turns for this wiper to go from one end to the other. So as I'm turning the outside, I don't have any appreciable change of resistance whatsoever between my pins 1 and 3, as you can see, yes? So what I'm going to do is now show you something right here. I'm going to hook this up to the middle pin. If you can see that a little bit more clearly, like so. So I'm going to have the red in the middle and the black on one end. It doesn't matter which end. I put it on the far end so I can get a better view of the screw terminal. And notice my display. My display is presently showing me 302 ohms. So that means between pins 1 and pins 2, pin 1 and pin 2, I have 302 ohms. I should have the balance of the ohms on the other side right here and let that stabilize. And I have 201 ohms. So does the 302 plus the 201 or 200 add up to 500? It should. This is very similar to the lab that I had set up for you with the previous potentiometer. So it turns out as we go to look at this, and sometimes some authors will call this pin A, pin B, and pin C, or pin 1, pin 2, pin 3, just depends on the author. So this is what you're going to find. If R from A to C equals 500 ohms, then what you're going to be able to conclude that R A to B plus R B to C is equal to 500 ohms. Meaning from the outside pin, the left pin, from the left pin to the middle pin, whatever measurement that is, I can add it to the middle pin's measurement to the far right-hand pin, and those two numbers will be very close to my total. Actually, they generally will add up to be slightly more, and there's a reason for that. Okay, they won't be precise because that wiper thing that moves inside that track is not a needle. It's kind of blunt shaped. So it's kind of like this. If this were the resistor element and the wiper inside is not like this pen, it's not a needle point like so, it's a little more blunt like this end of the pen. And because it's a little more blunt, it will read a reading that will show R A to B plus B to C being slightly more than 500. So we'll demonstrate. And you may also find it easier if you put it on your breadboard. Notice that the spacing between these pins is not, the spacing between the pins is not physically identical. All right, so if I line them up with my jumper wires on the board in this fashion, go ahead and insert this into the board like so. And I'll do this at an angle so you can kind of see how my jumper wires are lining up. And hopefully, is this a good view for you all? Like so? What it is that you're seeing is I have one jumper wire that is on the breadboard that is attached to pin A. I'm using the red jumper wire on the breadboard that is attached to pin B. And I'm using the third jumper wire on the breadboard that is attached to pin C. And I'll try to hold this steady while the camera auto focuses. There. Kind of like that. And once you get the alignment of the jumper pins correct, then you can push this down onto the breadboard. I won't push it down all the way yet. I just want you to get a good view of how to line up your jumper wires with respect to the potentiometer. So give me a thumbs up when you think you've gotten there. Okay, Gabriel, you're good. Rebecca, good. How about Andrew and Kyle? You have that potentiometer on the board similar to this?
We're putting one more in right now.
Okay. Pedro, Wenbin Lau, admit.
Okay,
If
we're
you allow. Hi, Wenbin Lau. Hi, welcome, welcome, welcome. Are you with us? Yeah, turn on your microphone and turn on your webcam if you would, please. Pedro, how you doing? All right, good, cool. So once we have that alignment in place, I'm now going to push this little puppy down so that it's firmly on the board. You should not be able to see the pins anytime you're using this. So the only time you see the pins is when you're lining up your jumper wires to make sure things are where they're supposed to be. So I'm using the black wire on the left as pin A, using the red wire as pin B, and using the black wire on the far right as pin C. So if I go to get my multimeter, and I to hook. Let's go measure the outside first. So if I go to measure the outside right here and right here, get those wires out of the way, like this. And what does my meter say? My meter says I've got 0.5 k ohms. Is 0.5 k ohms my 500 ohms? That's half a kilo. Kilo is 1,000, so 0.5, half a kilo would be 500 ohms. And as I've said before, if I go to rotate this particular shaft of the potentiometer, I am not going to get any appreciable change. I'm not going to get any appreciable change. See, you can see the tip of my screwdriver rotating, and there's no change on my outside pins. You should be able to see the same thing. I'm rotating a lot, and at most, what, 499, 1 ohm? Yeah, it's not really changing appreciably. So that's what we should realize when we go to play with the outside pins. So if you're able to confirm 500 ohms, can you give me a thumbs up? Okay. Thank you, Pedro. Wen Bin Lao, turn on your webcam if you would, please. Gabe, were you able to measure your 500 ohms on the outside pins?
Yeah.
Good, cool, excellent.
Well, I only got 4.9.
4.9?
Yeah.
Oh, interesting. I thought I gave everybody the same potentiometer.
Mine's 4.8.
Could you show me the display of your digital multimeter? Just hold it up to the camera. So, oh, okay, so Pedro's is 0.483, meaning it's 480. And Gabriel, yours says 490 without a decimal point, correct?
Correct.
Okay, so it's 490 ohms. I heard you say 449 or 4.9. I misunderstood you, sorry. So yeah, we should be something very close to 500 ohms. Pauline, what do you measure on your outside pins? Pauline needs to unmute her mic.
There you go. Sorry.
There you
about
go.
that.
Yeah, sure.
Well, it turns out that I have 0.525, so I have exceeded the 500 k ohms. So.
Oh, wonderful! You got extra 25 ohm bonus there. Wow.
Amazing.
Okay, so each of us has a slightly different reference outside measurement. I saw 480 something, 490. I have a 500. Sometimes it's 499 on my display. Rebecca, how to work out on yours?
I have 0.495.
Okay, so 495. And Andrew,
I got 488.
488 ohms. Okay, Mr. Lau, we are playing with the potentiometer that I gave you in your kit, putting it into the board and measuring the outside pins with your ohm meter. So when you have that up, put yourself on the microphone, let us know what you've got. Okay, now the fun. We'll see now, hook up your red alligator to the middle wire. So now what we're measuring is the amount of ohms between pin A and pin B. Whatever that number of ohms is, mine happens to be 480 something. That's rather high. I'm going to adjust this so that it's something less. Move my arm out of the way. You see my ohms changing? I'll stop it. I'll stop there. That's a good stop point. So show me, no, you don't have to show me. Just tell me what you're measuring between pins A and pins B, as long as it's not 500, something less than 500.
231.
231, good. Okay, hold that. What you want to do, Andrew, is you want to write down 231 on a paper. And then, Rebecca, what do you have?
1 second. Hold on.
Okay, it's all right. Pauline, what do you have?
I'm sorry, I'm still reading 525, so.
Okay, yeah, just put the little,
yeah.
put the adjuster thingy in there, and it'll start descending once you start spinning it. If you feel some resistance, then start spinning the other way, but you should see the display of your multimeter start changing pretty quickly once you get some kind of a change. Gabe?
301.
3-1 is good. That's a good stop point. Hold on to there. Pedro, what do you have between A and B?
215.8.
215.8. Ooh, that's very nice. Wen Bin Lao, have you been able to set up your potentiometer yet? You can unmute your microphone so we can hear you, please. Let me check the chat. Hold on. He might be communicating. Oh, Mr. Lau has no camera. All right, but do you have microphone so we can at least hear you speak to us? He's figuring that out. Okay, unmute.
Okay,
there you
good.
are. All right,
Can you hear me?
excellent. Excellent. Thank you, Mr. Lau. So we're working on this potentiometer, which is one of the parts that you were given. And so we put it on the breadboard. We're connecting a wire to the outside pin, wire to the middle pin, wire to the other outside pin, and it looks something like this. Let me hold this up to the camera so you can see more clearly what's going on. Those are the pins of your potentiometer, and we want to line it up with our breadboard to line up with our jumper wires that are on the breadboard. So once we do that, we're able to keep the potentiometer on the breadboard with maximum stability while we go to spin the shaft with our supplied nylon screwdriver. So the screwdriver, I would recommend holding the thumb over the potentiometer, and the potentiometer should be positioned ideally near the periphery of your board, so you have maximum access to reaching the brass screw head in order to make those turns. So that's here and here. So I didn't want to turn it too much. My meter turned off, so turn that back on. And do this guy here. All right. So that's where I'm at, and I have, okay, I did turn it slightly. So Co has 388. So getting back to Rebecca, what were you able to measure?
0.399.
399 is a good number. And Pauline?
I brought it down to 0.376.
Okay, 376. Perfect. So Rebecca at 399. Then we had, I think that's Andrew. Andrew at 231. Gabe
Yes.
at 30. Yeah, Gabe at 301. Pedro at 215.8. Co was at 388. Pauline at 376. 4, 5, 6. And Wen Bin Lao, when you can get set up and give us a measurement.
I would get 295.
295 between A and B, between the left pin and the middle pin. Correct.
Middle pin. I create.
Yeah, that's what I have as this outside pin. The left pin we'll call as A. The middle pin we'll call as B. And so between A and B, this is the middle pin. These are the measurements that your classmates have called out. So just looking for yours when you have a number that you feel comfortable in sharing with us. Next. So what we're going to do next is we're going to add each of these numbers to what you're going to measure between the outside, the middle and the outside pin. So all you have to do is just move this black lead over to here, leave the red lead in place. So now, is my digital multimeter hooked up to measure between pins B and pin C? And as I'm measuring between pin B and pin C, what does my display show me? COES display shows me 111.1. And when I add these two numbers up, I'm going to have 499.1 ohms. So why don't you measure, measure. Yeah, okay, so Andrew, what's your number?
276.
276, and we add these two numbers up, they give us 500, right? Cool.
Yes.
Rebecca, what did you measure?
100.
100. So the 100 plus the 399 gives you 499, which is pretty much 500 ohms. And Gabriel? He's measuring. How about Pedro?
271.
271. Added to this gives you very close to the 285. Actually, the 485 that you called out originally. So in most cases, it's going to be slightly more than what your original outside values were. Gabe, do you have a number for us yet?
Yeah, 206.
206. When we add these two, yeah, you're clearly over 500 ohms, so it's 507. When we add these, when we add,
206.
yeah, 200. Yeah, sorry, 200 and 200 and what?
2006.
It's not 2000.
Yeah, so my first one was 3017, and then my second one is 2006.
Show me your meter. Let me double click this to full screen mode. Escape. Huh. Okay. Yours is special. Yours must have ended up somehow being a 5K ohm instead of a 500 ohm. Odd. Is it the same color as the rest of ours? They should have been.
What was that?
Is the potentiometer the same color as the one that's on my screen?
Yeah.
Okay, all right. That's fine. And Pedro, we already called yours out. Pauline, what do you have? Oh, you got to unmute your mic, dear.
There you go. I have 145.
145?
Yes.
Okay, 145, and so that exceeds the 500. I think you called out some 525 before.
Yeah.
So that puts us pretty much where we very close to where we want to be. When Bin Lao, do you have a measurement between BD?
218.
218 plus your called out 295 puts you over 500. So yeah, so this is a good test of the potentiometer. So what you're going to be using this for are several things. If you needed a resistance that was exactly 285 ohms, well, let me tell you, there is no fixed resistor in our kits. There's no resistor in our kits that's 285 ohms. So but you needed 285 ohms for a particular circuit. How are you going to get it? The way you're going to get it is to use a what? A potentiometer. And how are you going to use the potentiometer? Of the 3 pins that you have, you're only going to use 2 pins. You're going to use the middle plus either of the outside pins. So as you can see in our first set of measurements over here, 399, 231, 301, 215, 388, all of those came about because you adjusted the brass shaft at the end of the potentiometer, dialed it into something. Well, if you wanted to dial into something very specific, let's go ahead and try that now. Let's go ahead and see if we can all hit. I'll think of something for you in a moment, Gabriel. Looks like you get a 5,000. So all of us, our target resistance that I want you to tweak this to will be 285 ohms. And for Gabriel, we're going to have you do this. We're going to have you hit 2550 ohms, okay? So it doesn't matter which two pins, as long as one of the pins is the middle pin. So I'm gonna measure between pins B and C, and I'm going to hold my potentiometer and use my screwdriver. Keep an eye on my meter. And I'm going the wrong way, right? I'm going down. So I'm going to turn this upwards. And remember, it takes a good 12 to 15 turns before this thing goes from one end of the the potentiometer to the other. And I will dial this in right up to, and slowly get as close as I can to the 85.
Okay, I move.
All right, as close as I'm going to be able to get. I have 285.2 on my digital multimeter. And when you feel you've gotten close enough, then show me your displays, and I'll sign you off on the potentiometer lab. So, Andrew, 285 ohms. Very good. Rebecca, nice. Rebecca,
That's Kyle and I.
285 ohms. And Pauline, I see 284.5. All right. And Gabriel, I see our targeted 2,850 ohms. Pedro, could I see your multimeter, please?
The screwdriver or whatever you give us,
Yes,
it's not
yes.
working with mine.
Mm-hmm.
It's not turning the knob.
Let's see. It is, if you look at the screwdriver at its end, you should be able, if it's not damaged, I made sure all of those were pretty clean before I pulled them out of the drawer bin. You should have it should be shaped as a slotted screwdriver at its very end. And I'm holding it so you can see just the tip of the slotted screwdriver. So
I had the same problem. I had to go get a metal screwdriver because the piece, like this plastic, would keep bending and it won't twist it.
okay, yeah. So here's the thing: if you're on the brass shaft and you feel resistance, don't keep turning, because the brass and the innards are stronger than the plastic screwdriver, and it will end up deforming and damaging this. So spin in the opposite direction, because what has happened is the wiper arm inside may have already gone all the way to an extreme, and then once it goes to the end, if you keep spinning or you try turning, then you're going to damage the little plastic screwdriver. I use a metal one. I use a metal one only because it's just, I have a spinner tip on the end, and so it's just easier for me to just do that and spin. So use whatever is necessary in your toolbox at home to make the adjustment. Okay. But that is the lesson of the potentiometer. Wen Bin Lao, do you have something for me?
Yeah. I got it to 280.
You were able to adjust it? Okay, that's good. All right. All right, this is great.
286.
So 286, lovely. 286 for Lao. Fantastic. All right. Now, so when we're ready to build this onto a board for a very specific amount of ohms, remember, you will only use 2 pins. You'll only use either the A and B pin, or you'll use the B and C pin. When you go to set a potentiometer on a board, my recommendation is set the potentiometer near the periphery so that you have access to the screw, the brass screw head. If, for example, I bury my potentiometer over here on the board and I have a bunch of other wires crisscrossing my circuit build like so, and then another wire somewhere over here crisscrossing the circuit wire like so, it may be harder for me to access the brass screw head when it's in the middle of the board. So try to plan your usage of this guy in such a way that it's near some periphery, and then use your jumper wires to jump to wherever you need the variable resistance to exist on your breadboard. Okay? Okay. All right. That's great. So any questions that we have regarding potentiometer? Potentiometer has how many pins?
3.
3 pins. And what kind of a resistor is it? It's a variable resistor, and it differs from the first potentiometer we gave you. The first potentiometer we gave you was kind of a circular shaped device with 3 connecting pads to it, and you turned a knob which wiped. And this is fairly simple. It was a one turn to be able to go from one extreme all the way to the other. This one here is a fine tuning potentiometer between 12 to 15 turns to go from one end to the other. Okay? Okay. Let me go ahead and turn off my meter because that was beeping at me. So that part there is done. All right. Next thing I want to talk about is our TINA software. So let's take a look at Canvas. So open up Canvas if you would. And open up our class in Canvas. I'm going to do a share screen in a moment. Okay, so let's go to share. Let's go here and here. Okay, can everybody see my Canvas screen now? Oops, am I on the right one? Video. No, I should be on my share screen. Why is my video on here? Are you still looking at the potentiometer drawing that I did, or are you looking at my Canvas screen?
The Canvas screen.
Okay, good. You see the Canvas screen. That's dynamite. All right, so I'm going to lower this a little bit so you can see the top of my Canvas screen. And what's interesting on the Canvas screen is this. Not everybody can see Studio. Can you see Studio on my screen?
Yeah.
Yeah. See, it does exist. I have modules, home, modules, announcement, discussion grades, syllabus, Confer Zoom, and Studio. Now, do your screens end at Confer Zoom and you don't see Studio?
Yes.
Horrible. Okay, I don't know why, but I will try to find out from our friends at IT and Canvas support as to why the students can't see Studio, because when you click it open, it's intended to be, the intended use for Studio, as this opens in just a moment, is to be a repository for any videos that we happen to have in here. And what's nice about having a repository is that through Studio, we're able to get closed captioning also. So sometimes if I happen to speak a little too quickly, then sometimes the closed captioning, as long as it translates my verbiage accurately, then it gives you additional backup for better understanding the lesson that lot. Now, since we kind of discovered that that was not working so well, that Studio was not working so well for students, what I've done was in the TINA, the week 9 TINA screenshot, if we open that up, there is this blue box with a white triangle in it. So what I'd like to do is do another roll call and make note who can actually run my training video, the Series 2R tutorial MP4 video in the week 9 TINA TI circuit screenshot. Can you press this and tell me that it works? So Rebecca, are you able to see this video on this page in Canvas?
Yes.
Okay, good. Can see. All right. It's a yes. Okay. And Mr. Lau, does the video run on your screen?
Screen.
Gabriel?
Yeah, I'm right now on it.
So just tell me it runs, yes?
What do you mean it runs? Like if I click play on the blue screen?
Yeah, right. It runs. Okay, good. Andrew and Kyle?
Yeah, ours works.
Okay, yes. Yes. Pauline, does it work on yours?
Yes, and I was actually able to do a couple of the assignments that you've
Cool.
assigned.
Cool. Okay, I'll catch up with those,
Yeah, I see it.
very shortly. And Mr. Lau, the video runs okay on yours?
Yeah, runs okay.
Wonderful. All right. That particular video is like maybe 18 minutes. I don't think it's particularly long, but takes forever to load. So as long as you can see it, we will continue using that format. But I think what we may end up doing is posting these on my YouTube channel. If I can port these over to YouTube, that way you can view these without ever having to get into Canvas. Anyway, we're experimenting with several things, but at least now I know that if it doesn't work on YouTube, if I can't get it over that way, for sure I can get it videos where you can see it in Canvas, even though you don't see Studio. Cool. This is good. All right. So we had, go back to home. And some of you have already done this. Not everybody has completed this yet, but some of the things that we're working on this week are the Series 2, Series 3, and Series 4 TINA circuits, and the Series 3 is a 3 resistor version. Let me go ahead and magnify this. Okay, so as I've said, some people have already completed this exercise. Does anybody have any particular questions regarding this software? Is everybody able to pull down the desired elements and be able to construct this? And I think one of the things that maybe in my video, I said that because the resistor looks like it's connected, you want to make sure that any device is physically connected by grabbing the resistor and moving it up or moving it down, and make sure that the wires follow the device. So you want to make sure that they don't just appear to be connected, because if your numbers don't jive with your calculations, it's probably because there's a wire that's not physically connecting somewhere somehow, okay? So that's the only hazard to be concerned about. But we will be using TINA as a backup to double check our work. So I will be going into a different exercise with you now. So you're going to need your calculators, because we're going to do some circuit analysis on paper. And let me come back over, stop the share. And we're back over to my dot cam. Move this out of the way. this out of the way. Okay. So we started to talk the last time, and we're going to continue this with parallel series circuits. So it's not series parallel, but this will be parallel series. And what I mean by that, I'm going to show you a circuit. And let's go ahead and do this guy, this guy, this guy, this guy. We'll have a voltage source. Come up here and come over here. Create a resistor. Create another resistor. Come down here. Create a node. Call that node B. The one at the top, call that node A. And then over here, resistor, 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 another resistor, 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 down to here. And we will call this a 27 volt source. We will call this R1, R2, R3, and R4. Oh, somebody's clicking on. Let's see who else is here. Let's try this. Mr. Cortez, welcome. We can see you. We can see you in two different places. If you've been waiting long, I apologize, but we only need to see you in one. And here, 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 here. Enter full screen, speaker view, and there. Okay, is this a little better? Or was there any change?
Looks good.
Okay, so what we're going to do is to show you how we go to analyze this circuit once I put in some resistor values for all of the considerations that we're going to be interested in. And so the considerations we're going to be interested in will be for R1, R2, R3, R4 totals. And we would be interested in the following information. Voltages for sure. Current is for sure. And resistance as well. So there's our VIR chart. Now the resistor values that I'm going to have you think about for this particular analysis will be as follows. Let's go ahead and put R1 up here will be 780 ohms. So that's 780 ohm over here. I will have R2 be 1.5 K ohms. So I will have 1.5 K ohms over here. R3 will be 560 ohms. I will have 560 ohms over here. And then R4 will be, let's say, 330 ohms. This will be 330 ohms. My voltage source is given as 27 volts, so I will write my 27 volts right there. So that's the information we're going to start with. Why don't you get that drawn, written down, and I'll catch up with Mr. Cortez. So Mr. Cortez, welcome to our discussion. I see you logged in 3 places. Only need to hear your voice in one of them. How are you doing, sir? Christian, can you acknowledge, say hello? I see you as part of our group, but I don't hear you. Let me check the, you can also type a message in chat if your microphone and camera are not working, but I see 3 separate logins for you, but I don't hear any response. So I'll keep trying. There may be some technical issues on your end. Hopefully you can hear us. All right. So how do we go about working this particular guy out? Working this particular guy out will be done this way. The process, there's a process. Let me find the right pen here. All right. Process. The process is called circuit reduction. That's the name of the process. How is done by redraw circuit. The why, to simplify. Okay. So the process of analyzing what we have here can be described simply as circuit reduction. The how that we're going to implement is by redrawing the circuit. And why are we doing this is to simplify, because right now we happen to have 4 resistors. We have to simplify this to something a little more understandable. And so my recommendation is, since I have this drawn here, I'm going to redraw this. I can redraw it to the left, right, doesn't matter. Some of us find it very convenient to draw it directly underneath the original circuit. So I will create my node A. Here's my wire coming out here. Here's my voltage source. And this will come down here. Here will be my node B. And this will come over to here. This will come down. This will come over to here. This will come up like so. But what's interesting is instead of these 2 resistors being separate, you can see that R1 and R2 have what electrical relationship? Are they in parallel or are they in series with each other, R1 and 2? Rebecca, what do you think? Microphone.
They're in series. Sorry.
They're in series. And we define that they're in series because there is only one current path between R1 and 2. So because they are in series, could I combine these 2 into a single resistance? And I will do so. These will become one single resistance that we will label as REQ1. And what EQ stands for, EQ stands for equivalent. Meaning that this single resistor represents the sum of these 2 guys. So if you go to add these guys up very quickly, you're going to have 780 plus 1,500, yes? So 780 plus 1,500 gives you some kind of a total. You need to do that on your calculators. And 780 plus 1,500, the fastest way to add. So Pauline, what do you have?
I get 2.28 kilo ohms.
Excellent. 2.28 kilo ohms. So does everybody see how we handled the first branch, which had 2 series resistors that became a single equivalent resistance? We name it as REQ number 1 because over here in a moment later, we will have an REQ number 2. So the subscript number 1 and number 2 differentiates first branch equivalent resistance from the second branch equivalent resistance. So now I'm looking for a total for R3 and 4. R3 and 4, as you can see, is a single current path, which puts R3 and 4 in series with each other. Therefore, if I wanted to combine them into a single equivalent resistance, I simply add these two numbers. And when I add these two numbers, Gabe, what value does R3 and R4 add up to be? Unmute your microphone and give us your answer.
890.
800. How many people agree with 890? Raise your hands. Yes. This is good. 890 ohms. And we would write that down. So far, so good. Now, our voltage source still hasn't changed. It's still 27 volts. So in this very first step of the process, what is the process called again? It's called circuit reduction. How are we implementing the process? We are by redrawing the circuit. And the purpose of doing so, the Y, is for what purpose? To simplify. Have we simplified the 4 resistors now down to a 2 resistor circuit? Yes. Then what do you think the next step is going to be? We're going to redraw again. Here, oops. Here is my point A. Back over here. Here is my point B. And I will have these two guys combined. So what is the relationship now between REQ1 and RE2 as I've drawn in this middle circuit? Question goes to Andrew. What is their relationship to each other? Are they in series? Are they in parallel?
They're in parallel.
They're in parallel. So what I'm looking for is these two resistances, the equivalent resistances, coming up to be some kind of a total here. So what would be one method that you could use to calculate these guys in total?
You could use the reciprocal theory.
You can always rely on reciprocal. Reciprocal will never let you down. You also can remember that because these are two values, you could also use product over sum. So you could take 2280 plus 890, divide by 2280, 2280 times 890 over 2280 plus 890. So you can do product over sum, but there's no other shortcut that we can use. So I would recommend, let's go ahead and stay with reciprocal method. Now, I would like each of you to do a calculation, but actually before you even touch a calculator, can you guesstimate, can you have a gut impression of what those ohms ought to be? Are they going to be higher than this? Are they going to be lower than this? What do you think? Pedro, what do you think? What do you think my total between these two values is going to end up being?
Lower?
Lower than what?
Than the overall resistance?
Well, we're looking for the overall resistance, but you almost have the right words. What I was hoping to hear you say, and let's see, Kyle, what do you guesstimate the? And I'm not looking for a number. I'm just looking for a concept.
I think it's going to be lower than the. I think it's going to be lower than the REQ1.
For sure, it's going to be lower than REQ1. I'm looking for something else. Yes, Rebecca, you have your hand raised.
Shouldn't it be lower than REQ2 because shouldn't the total be lower than the lowest ohmic branch on a parallel circuit?
Precisely. That's the verbiage that I'm hoping each of you have emblazoned to the back of your retinas, okay? That the total resistance of any bank of resistors. Remember, the nickname for parallel circuits is they're called banks. This is one branch, this is a separate branch. And the total for these guys must always be less than the lowest ohmic branch. So it's got to be less than the 890. That's the verbiage that I want for you to instill in your hearts, to be able to just, okay, boom. I don't know anything about the actual number, but I do know it's got to be less than 890. So if you calculate something more than 890, boom, there's something wrong in your calculations. So now that you've had some time to do these calculations, I'm now going to call out for an actual number here. So I'm going to do reciprocal plus. Okay, I'm looking for the very first digit of your R total. Christian, are you with us?
Yes.
Hey, there you are, Christian. Fantastic. Have you been following this along with us?
I just joined like 10 minutes ago because it wouldn't let me join earlier. I don't know why.
Yeah, sorry. We need to start closer to the beginning of the hour. And so once I start talking, I apologize. I may not see somebody in the wait, and so part of the delay was waiting for me to notice that you were in the wait room. So as a recommendation for all of us, my friends, is really try to start right on the hour, and that way I can go through the login. So anyway, I'm glad you're with us. We're working on this particular exercise. This is being recorded, and so you'll be able to see the recording later on, but nothing like participating with us. So I'm glad you're here with us. Let me continue. So Wenbin Lao, do you have a total resistance number that you are happy with?
No.
No? Okay, keep working on that. Pedro, do you have a total? Okay, don't shout out the answer, but Pedro, give me the first digit of your answer. First digit only.
6.
Good. All right. That's good for now. And how about Gabriel? Do you have a total you're happy with?
2.
No, the second digit is not going to be a 2, and neither is the first digit. So I'll show you how to work that out. Pauline, do you have the second digit for us?
Second digit is number 4.
The second digit is a 4. Very good. So the first digit is a 6. And then we have a 4. I'm looking for the third digit. Rebecca, you have the third digit for us?
0.
0 is correct. Excellent. Now I'm looking for the digit after the decimal point. Kyle, do you have that?
No, I do not. I'm still doing the calculations. I got it wrong the first time.
Andrew?
Yeah, I got it wrong too. I'm working it out right now.
Okay.
Where I messed up.
So let me show you what you need to do in order for us to achieve the desired result. We have these two guys in parallel with each other. So as a reminder, the keystroke sequence, let's do this with decimals first, just to keep it simple. This is 2,280, yes? And you have to hit this reciprocal key, which is an X -1. In some calculators, it might be a 1/X key, but somehow you need to engage. This is called the reciprocal key. You need to engage this function, and it may be a second function on your calculator. So you might have to hit second and boom, one of these. But however it's done on each of your calculators, you take the first number, you reciprocate it, and then you do an add. Then you take the second number and you also reciprocate it. And then you hit equals. Then you hit the reciprocal one more time. And then you hit equals. So that is your keystroke sequence to successfully calculating this number plus all the digits after. So do that now.
Oh, okay. I see where I messed up now.
Okay.
I got a number after the decimal.
Okay, what's your first digit after the decimal point, Kyle?
I got a 1.
1 is very good. Okay, so that is correct up to this point. And Wen Bin Lao, do you have the next digit after the decimal point? Mr. Lau? You need to unmute your microphone. Gabe Orozco, do you have that number? You need to unmute your microphone if you're responding. Andrew?
I got it. It's going to be a 3.
It's going to be a 3. And that would be correct. And this would be followed by the omega symbol, yes? So the important thing to recognize here on your calculators, you should end up with a 640.126183, something, it keeps on going. But what you're going to need to keep in mind is properly rounding off. Now, our standard is we're going to be rounding off to the second digit after the decimal point. You always need to look at the third digit for guidance. And the rule of thumb was, if that third digit is 5 or more, then what you need to do is round up your second digit. And that's why the 640.12618 becomes a 640.13 on your answer sheet. Everybody clear on that? Okay, okay, cool. So now we can fill this guy in over here as 640.13 ohms. Yay, terrific.
I'm getting a different answer for that reminder you put up there. Yeah, I keep getting a 35.88.
You're typing in 2,280 reciprocal plus 890 reciprocal equals, and then you hit reciprocal, and then you hit equals.
Yeah.
And what does your calculator show you?
35.88.
And who is this?
Gabriel.
Gabriel, okay. Gabriel, where's your, oh, there you are. All right, so Gabriel, show me your calculator. All right, so why is it answer squared? Why is it answer squared? Squared is not the function we use. I see an answer squared. There's no square in this whatsoever. This is an x negative 1 or a 1 over x function on your calculator. So yeah, you're going to need to...
Oh, I see what I was doing. I wasn't using the second F. I was just clicking the x negative 1.
Okay, so as I verbally pointed out on my screen, yeah, as I verbally pointed out, however you get to that reciprocal function, some of you may need to hit second and then this function. It just depends on your particular calculator. I'm not going to write out seconds. I'm not going to write out this 1 over x. I'm just going to use the standard x negative 1. But that's the process you need to learn on your own calculator, how you get here, okay? So once you do the recalculation, can you go ahead and show me on your calculator your final result? And the answer is 640. Okay, perfecto. I see the reciprocal sign, answer 1. Excellent. Feeling better, Gabe? I'm feeling better. I bet you're feeling better. That's great. All right, my friends. Now, back to my screen. All right. We have 3 columns, 5 rows, that's 15 cells, and this is all we filled in so far. We've got to knock out the rest of these. So how do we go about doing this? What should we do next? Somebody raise their hands. Let me know what's going on. Yes, Rebecca.
We can solve for I total
This guy right here.
Yeah.
And so this I total represents our most recent circuit, I think. We happen to have in our most recent redraw, the voltage source hasn't changed. It's still 27 volts. Point A is still on top. Point B is still on the bottom. We've completed our process, circuit redone. We've redrawn to simplify. We've got 4 resistors down to 2, down to 1. It don't come any simpler than a single resistor, R total. So Rebecca says we can just use Ohm's law to take the 27 volts and do something with it with the RT in order to calculate the current. And so as a gentle reminder for everybody, since it's been a little bit of time since we last chatted, there's your Ohm's law circle. And so if I am looking for I, what do? I cover the I. I would be equal to, what's left over is V over R, yes? So could we go ahead and everybody do that now? Take the 27, divide by the 640.13 or whatever your calculator has. I'm going to use all of it. So 27 divide by up here, boom, and enter. And so your suggestion is spot on, Rebecca. That's excellent. And the first digit of the answer, Rebecca, what do you have?
4.
Is a 4. 4 is a good number. We will write that down. Pauline, do you have the second digit?
Second digit is 2.
Second digit is a 2. That would be correct. Third digit, calling out to Gabriel. Do you have that third digit? The decimal, the digit after the decimal point.
I was going to say because it's decimal. And then 1.
Okay, would be a 1. That would be correct. And then the second digit after the decimal point, Christian, do you have that for us?
I rounded it up to an 8.
You rounded it up to an 8. That would be correct. And my units on this Pedro would be what?
Milli.
Milli is correct. And my electrical quantity would be what, Andrew? Milli what, Andrew, is the question.
Amps.
Milliamps with an A, like Andrew, huh? How about that?
Yeah.
Oh, hey, all right. Everybody in agreement? We have 42.18 milliamps, yes? And what your calculator should show you is all these giblets after the 0.7. So it's a 0.179, blah, blah, blah. You look at that third digit, it's more than 5, which means you have to round that 7 to become a 0.18. Is everybody clear on that process? Cool, this is great. All right, now that we have our master current, could I write that information here so that I can see it? Remember, this is positive on this side, this is negative on this side, and the current flowing in this current circuit right now is 42.18 milliamps. Yay, that's our I total. So we'll just go ahead and write that in. So have we thoroughly analyzed this third circuit for total ohms, total volts, and total current? There's nothing else for us to do in this particular guy. Everybody happy with that? All right, so now we are looking at 8 more squares to fill in, 8 more cells. What do we do with this? Who's got an idea? Where do we start?
Well, isn't the voltage the same in all of these? Was there parallel?
Who said that? Gabriel?
Christian.
Christian, yeah, Christian, yeah, you're right, absolutely. So if we take this 27 volts, the voltage is the same because this is a parallel circuit. So what do I do with that 27 volts? How's that help me fill in anything over here?
Divided individually by the resistances.
Divided individually by the resistances. Okay, so we can do voltage divider as one method of filling in some of these. That would be a good suggestion. Does anybody else have we can do this several different ways. I'm just trying to see how many people have how many different kinds of ideas. So dividing that 27 volts into the resistances to find individual voltages would be one method. What would be another method to fill in some of these numbers? If we have found one current, have we found all the currents?
Yes.
If we found this current, do we take this current and fill this in?
Yes.
Yes.
That would be a no, my friends. And I'll tell you why. You would fill this in only if this was a series circuit. As you can see, the original circuit is not a series circuit. So because you find I total, you have found I total, and let's go to the middle circuit so you can see this a little better. I total flows from the source, and it is indeed at this point 42.18 milliamps. It flows to this node B. When it flows to node B, do you see that the current will split at node B and go up two different paths? So this 41.18 can't be the current that flows up through here, and it can't also be the current that flows up here because it splits. Part of the current, part of that 42.18 flows up in this branch, and part of it flows up through this branch. So if you can understand that this 42.18 milliamps that flows out of the source to node B splits, it cannot be filled in on all of these cells. What else can we do? That was a leading question. That was, I didn't mean to cause anybody to fall into a trap or anything, but that's what we call a leading question. When you're at a job interview and the job interviewer asks you the very same question and nods his or her head, oh yeah, we found this current, now we can fill this in, right? And the person is nodding their head up and down, and I'll show you what I mean. So here we are. You found the total current. Because you found the total current, we fill in all the currents, don't we? Yes, yes, yes. And you're supposed to say no, 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 because you know better. Okay. So that being said, because you know better, what would be another way for us to do this? We have one suggestion that was valid. Voltage divider is one method to split this up and find the voltages. What else can we do? Another idea, because there's several different ways we can do this.
You divide voltage with resistance.
Who said what?
You divide.
No, who?
Gabriel.
Gabriel. Okay, so Gabriel, what are you suggesting?
You get your voltage and you divide it by your 780 amps, and you just keep going down.
We don't have 780 amps.
I mean, ohms.
Ah, okay. We take this 27 and divide by 780.
Yes, correct.
Ohm's law.
I think all the voltage is the same.
Yeah, Ohm's law won't allow us. Ohm's law won't allow us to do that because that 27 volts is not solely across 780 ohms. That 27 volts is across two resistors. So we cannot take that 27 and divide just by here, because that 27 is, as Christian suggested, part of that 27 is across R1. Another part of the 27 is across R2. So we can't take 27 divide by 780. So that aspect won't work because we don't have 27 only across the 780. You keep thinking, the more we think, the more we verbalize, the more we throw out there, the more we can discover what we can cast aside, and ultimately we'll get a method. Another method somebody would like to
do. You can do it on the second
suggest?
picture though, right? On the RQ.
Oh, hold on, I got Bolito coming in. Hold on. Where's Bolito? Bolito. He needs the meeting ID. Great. I sent out 2 emails. Oh dear. Hold on, my friends, just one moment. I don't want to leave anybody behind. Oh Lord. I think the easiest thing to do is probably, no, not here. Not here. Let's go here. And here. And not here. not here. Where did he come in on? He came in on Canvas. Okay, so on Canvas, Zoom, please check email, enter, and send. Okay, hopefully he will read his email and click the link that you all did and be able to join us. All right, getting back to some suggestions. Pauline, you have an idea?
Well, I was just reading the summary, series parallel.
Summary is a good place to be, yes.
So
What did you cover from the summary?
if IR1 equals IR2 equals IR3 on the series.
Correct. In series, the current that flows through R1 will be the same current that flows through R2. So
Correct.
that current through here will be the same.
Correct.
What can we do to find it?
So we do a current divider.
Yes, we could use that as an alternative. So there's, as I mentioned, there's several different ways we can do this. So let's take a look at methods. Methods of analysis. Methods of analysis after I-total. And so one of the methods suggested, there's Rolando. Cool, hold on, let me click on this. Come on, mouse, here. Come on, Rolando. And admit, there he is. All right, Rolando, thank you very much for joining the meeting. You can unmute your microphone and say hi to everybody real quick. And he's getting set up. But here, let's go ahead and reiterate what some of your classmates have suggested. So Christian has suggested VDF, voltage divider formula, to find VR1, VR2, etc. Okay, so use that. Number two, we can use CDF, current divider formula, to find branch currents. We can certainly do that. So those are two methods already. Voltage divider formula, current divider formula. We've talked about before. I won't take the time to review here because I want to give you the fastest, smartest, not hardest way to resolve this. So where we are, once we find the 40.18 milliamps that flows out of here, we can use current divider and do that, because current divider formula, if you remember, your IRX was equal to RT over RX times IT. A little bit of calculation to do that, but I have a simpler method for you. The simpler method is to use Ohm's law. Ohm's law. And what you want to remember about Ohm's law is that your Vs is equal to V1 equal to V2 in parallel. So your I1, not IR1, but I1, meaning the first branch current, is going to be equal to V1 over REQ1. Very simply, look at this circuit here. You can copy that down later, or again, review the notes and get that later, but look at the circuit here. Don't I have a simple parallel circuit? And you know from your notes, in a simple parallel circuit, isn't voltage, that 27 volts, the same across the first branch and across the second branch? We're not going to use that in the first circuit because I've got two separate series resistors, but don't I have a single resistor in this middle circuit in this branch, and don't I have a single resistor here? So if I wanted to find the branch current, couldn't I just simply use Ohm's law and multiply my 27 volts, excuse me, divide my 27 volts by 2.28 k ohms. Ohm's law. This divide by these ohms, won't that give me my current in this branch? Yes, it would. And that's what I mean here. I1, not IR1, but just I1, meaning the first branch current, is equal to the branch voltage divided by REQ1. So everybody with your calculators, take 27 volts and divide by 2,280. And you end up with a current. And that current shall be called I1. And I1 will be equal to the following. So I'm going to be calling out for the first digit. And Rebecca, do you have that first digit for me?
1.
First digit is a 1. And I'm looking for a second digit. Let's see. Pedro, do you have that second digit?
1.
Is also a 1. Very good. Now I'm looking for the digit after the decimal point. So the first digit after the decimal point, Christian, what do you have?
8.
8 would be correct. And now I'm looking for the second digit after the decimal point. Mr. Lau, do you have that? Would be a 4. That's correct. And that's milliamps. So are we in agreement? 27 divided by 2,280 gives us 11.84 milliamps that flows up through this branch. Yes? By the same token, we can calculate the current on this branch because we know the 27 volts here is also across 890 because this is a parallel circuit. So now can we take the 27 volts and divide by 890 and calculate the branch called I2? So I2 would be 27 and divide by 890. And I'm looking for the very first digit of this calculated current. Pauline, do you have that first digit?
First digit is number 3.
Okay. Rolando, how are you doing? Do you have this calculation for us? 27 divided by 890.
Yeah, it's 3.
Okay, first digit is a 3. Very good. Now I'm going to call out for the second digit. Gabriel, do you have that second digit? Unmute your mic, pal. Kyle, do you have the second digit?
0.
0 is correct. Now I'm looking for the digit after the decimal point. Rebecca, do you have the digit after the decimal point, first one?
3.
3 is correct. Now I'm looking for the second digit after the decimal point. Gabriel, are you with us? Do you have that second digit after the decimal point?
No, I'm still doing the math, sorry.
Well, it's 27 divided by 890. Those two numbers, okay? Everybody should have this. Christian?
3.
No.
4.
Okay. It would be a 4 is how we should round it up. And what are my units here, my friends?
Milliamps.
Milliamps. Okay, cool. So look at the second this middle circuit. This 2.18 milliamps splits at node B to become 11.84 current going up, and it splits to become 30.34 going up here. What happens at the top of the circuit? At the top of the circuit, doesn't this current wrap around, come to node A, and isn't this 30.34 milliamps here? And isn't it adding with 11.84 milliamps here? Won't these two combine to give me my circuit current of 42.18 milliamps? Is that right? Do those numbers add?
Yeah.
How about that?
Yes.
So what the current that goes into a bank has to equal the current that comes out of the bank. Are we clear on that? I will write this down. Current entering a bank must equal current leaving that bank. And bank, if you remember, was the nickname that was given for parallel circuit. So the current, the bank is comprised of these two equivalent resistances. 42.18 milliamps is flowing in. It splits apart into these two branches to become 11.84 and 30.34 milliamps. At the top of the circuit, they combine and they do add back to the original amount of current going back to the source. Isn't this a marvelous thing? And with this analysis, can we now bring some of this information back to the original? We started in our analysis with this, simplified to here, simplified to a single resistance. From here, we found our RT. Here we found our IT. We bring this IT information into the middle circuit. The IT we discovered split. Now we can take this information back up to the original circuit. And what information do you think we're going to take up here will be this. We now know the current that flows up here, and we now know the current that flows over here. The current that flows up here through between A and B in this middle of the circuit is my 11.84 milliamps, and the current that flows on the outside is my 34 milliamps, sorry, 30.34 milliamps. What's that tell you about what we can fill in here? Do I now know the current through R1? Yes. Do I now know with confidence the current through R2? Yes, because the current is the same in a series circuit. Over here on this branch, I have a different current, but I have two resistors in series, and because I have two resistors in series, isn't that 30.34 milliamps flowing through R3 as well as R4? Can I fill that information in my VIR chart? Yes. Yeah. So I will write 11.84 milliamps here, 11.84 milliamps here, and 30.34 milliamps here, and 30.34 milliamps here. There we go. The current column is now complete. What else is left to do is to finish calculating our voltages, yeah? And to calculate our voltages, wouldn't we employ a simple method of Ohm's law? Again, if I want V in my Ohm's law, don't I cover up the V with my finger? And that's equal to what's left over, I times R, yes? So I'm going to do the same thing here. If I want V, my V is equal to my I times my R. Do I have an I? Do I have an R in each of these rows? So I can do these calculations. So everybody go ahead and do these calculations right now. I'm going to call out names for answers in a moment. Oops. One, two, four, and then here times, okay, 1.6, and then here times this guy, and have 3.9, and then I have this guy times I have this guy here, 0.01. Cool. All right. Okay, first one. Let's take a look here. Okay. By raise of hand, who would like to offer the first one? Rebecca, go ahead and give us what you calculate for the first one.
9.24 volts.
9.24 volts is correct. Thank you. Who would like to volunteer the second one? Raise your hand. Let me get to a different screen. Come on, mouse. I can't see everybody. Mouse. Got too much stuff on my desk. I'm sorry. If you're raising your hands, I'm sorry. I can't quite see everybody yet. Okay. All right. So somebody raise their hands for VR2. Remember, it's only this current times this ohms. This current times this ohms. Pauline, what do you have?
17.76 volts.
That's the year our nation came into being, the year 1776. How about that?
Yeah,
You are correct.
right.
That is correct. Now, all right, who would like to raise their hands and give me VR3?
It's 1699.
1699, Gabriel, is correct. Thank you. And who would like to give me the answer for VR4?
$10.01 volts.
10.01 volts is correct. And let's see if those numbers make sense in our original circuit here. All right, so I will speaker view, and I'm actually going to write this information in on our schematic. So I have 9.24 volts here, and I have 17.76 volts here. Take a look at that first branch, if you would, my friends. I wrote 9.24 volts across this first resistor, 17.76 volts across the second resistor. Should these two voltages add this branch to give us the 27 volts that's over here?
Yes.
They do. Just like the resistors in series add, their voltage drops in series also add. So the 9.24 plus the 17.76 add exactly to 27 volts. Let's see if the same thing happens on the other side. On the other side, we had 16.99 volts. And then on the this resistor, we had 10.01 volts. And guess what? Doesn't the 16.99 add with the 10.01 add up to be the 27 volts that we started with on over here? Isn't that exciting? Cool. Guess what you're going to see for homework? More of this type of analysis, okay? And you'll be able to review all of our steps in glorious detail if they can give me my recording back in a timely fashion. It's going to be a huge upload, so it might not happen that you get it back this afternoon, but I'll try my best to make it available to you so that you can see what's going on with this. What to ultimately be able to do is to do this in Tina. So speaking of Tina, I am on Zoom, no, I'm on Canvas on my other screen. Let me go to our class 50 during the day. Come on, get there. And it's thinking Canvas is slow. Well, maybe Canvas isn't slow, maybe because I'm also doing Zoom in the background. It's using up a lot of resources. I think that's more the case. And checking on your progress of assignments. It's thinking. All right, while Canvas is thinking, does anybody have any questions regarding this process of parallel series circuits? To analyze parallel series circuits, and why is this called a parallel series circuit and not a series parallel? Here's the reason why. Take a look at the original circuit, and as you look at the original circuit, the current that leaves the source comes down and it sees node B. Between this negative plate, between the negative plate of the voltage source and node B, was there any series component in that wire whatsoever? None. Take a look at the current coming back from node A. From node A, the current coming back, is there any single series element in that wire between node A and the positive plate? The answer is no. So what happens with this particular circuit, it does split at node B and the currents combine at node A. It is fundamentally a parallel circuit, as evidenced by the middle drawing. But it has series elements in it. It has series elements in first branch, and series elements in the branch. For this is called a what? A parallel series circuit, in contrast to a series parallel circuit that we had done before. Okay, so that's the reason why we named this the way we do. Are there any questions as to how this is calculated? Okay, so now let me take a look at my TINA exercises. This is quite a ways. Okay, so week 10 TINA, I've got submission from Rebecca and Pauline, and nobody else has tried the week 10 yet. Let me take a look at the week 9 TINA. Come on, where is it? Is it here? It's on the wrong side, right side.
Professor Coe.
My friend.
I've been having issues downloading that program. I don't know if there's like an alternative way of doing it, but.
Are you using a Mac or a PC?
Mac.
It won't work on a Mac, unfortunately. I apologize, yeah, it just will not work on a Mac. The alternative program that we use is actually not free. What we use in the classroom is called Multisim. You may recall seeing that name in our computers in the lab. And Multisim is a more robust program. It is a very worthwhile program. I went and bought it. At the time I bought it, it was $45, but the current version for Multisim is $35. And it's an incredibly worthwhile investment because it is a more robust, more comprehensive piece of software than the TINA. But the TINA is free. However, the issue is neither one of those are compatible with the Mac. So what you're going to need to do is to try to explore what we call SPICE, S-P-I-C-E, SPICE programs. Explore, S-P-I-C-E, for Mac. Or try to get your hands on the borrow of a PC type machine so that you can do your TINA exercise.
I'm gonna see if I can borrow somebody's regular PC laptop. So
yeah, it doesn't take up much space. So if they're concerned, oh yeah, you're going to put a program that's going to hog my hard drive, it won't. It doesn't take up much space at all. It's a very small program, and it is tremendously worthwhile. So while I'm looking on my roll sheet here, I'm just going to mark down what I see for TINA submissions so far. So Rolando, you have a TINA submission. Rebecca has a TINA submission. So does Mr. Lau has a TINA submission. So does Gabriel, Andrew, Kyle, and Pauline. And so I'm concerned, let's see, so Pedro, where are you with your TINA?
I'm also going to need to go borrow a PC from someone.
Okay, all right, so Mac for now. And Christian, you're currently running the Mac, yes?
yes.
Okay, Mac. All right. And yeah, for the people who are on the call. Okay, all right. So now I know who's got the TINA. Yeah, you want to get on with that pretty quick because the circuit analysis in TINA and the circuit building is critical to helping to support the analysis that we're doing on paper. So what I mean by that is if I go home, and actually let me go and share my screen, share, and let's go here. What's that screen too? I need to find the correct screen. Let's not share. And now, can you see my canvas, everybody?
Yes, I see it.
Okay, cool. All right, so the TINA, the 2 circuit, which most of you have turned in, is this guy here. So it's the 2 circuit, the 2 resistor one. And for those of you who have not had a chance to play with this, I've moved the video over to the folder in Canvas outside of Studio where you can see the instructional video on how to construct this. But the key thing here is after we do an analysis as we've had on paper, you should be able to double check those measurements with TINA very, very quickly. Let me go out of here and go to here and home. And then I will go to, there's a very nice 3 resistor one and a very nice 4 resistor one. So here's the 4 resistor one. I'll show the 3 resistor one first since I happen to have that up. So here's the 3 resistor showing, it's a little bigger. All right, so it shows R1, shows R2, they're all different values, and meters in here. The V's measures are here, and your label is also designated in here as well. Then if I omit this, get out of here, and now go to 4 resistors, this is what the 4 resistor guy looks like. I have R1, 2, 3, and 4. So if we were building this circuit in TINA, then it would look something like this. Let me see if I can do this. Did I move it?
I have a quick question.
Please.
TINA.
Yes.
As I was doing the exercise, I knew that my wirings had been in contact correctly because when I do move the resistor, it does move accordingly. However,
Yes.
on the yellow numerical numbers there in your drawing, if you can go back to your drawing,
Mm-hmm.
not that one, your example. If you can go back to your example, and
Yes, what I'm going to do here in just one sec is find it here and move it over to this screen and then come back and share. Come on, share button. There we
I
are.
was just wondering if everybody else is having the same.
Well, let's go ahead and put the TINA. I have TINA running on my share screen presently, and so let's just build the circuit that I have. So I'm going to take this guy and place it here as an example. Get my resistor and place one here. Get my resistor, place one here. Get my resistor, place one here. Get my resistor and place one here. Okay, so move this guy up and I'm going to zoom in a little bit so everybody can see this a little better. How about if I go to 200%? Okay, so at 200%, can you see my components on my screen fairly well, everybody?
Yeah.
Okay. So I'm going to come here and I'm going to rotate this particular guy. Take this, rotate this particular guy, take this, rotate this particular guy, take this, and rotate this particular guy. And then now I'm going to connect everything. So I'm going to take my mouse pointer, put it on this little red X, and draw a wire connection between here and here. And then take a wire connection between here and here. And take a wire connection between here and here. And a wire connection to here. And a wire connection to here. And a wire connection to, yeah, there, okay. Not as pretty as I wanted, but anyway. So if I go to grab any one resistor to make sure that it is physically connected, I can click and pull it sideways. Do the wires on either end follow the movement of my resistor? Yes, they do, which means that it is electrically connected. Same thing up here. I take this, move this down, move this back up, move this out. The wires follow, yes? And as long as the wires follow, that means I have a good electrical connection. Touch this guy, go here. Touch this guy, come back. Touch this guy, come down. Touch this guy, go back. Take my voltage source, come out. So it looks like this is called the nudge. As I've nudged each component, I now have the assurance that everything is electrically connected. So was your question when we bring in a meter or something? What was your question?
My question is, when we do the analysis, when I do the analysis, and of course I've done it, calculated it first just to see that, you know, it jives with the numbers in the analysis. However, please go ahead and do the
okay. So what our classmates suggesting, when I come to analysis, on our pull down menu, click analysis, and I will come down to DC analysis, and I have a side menu, and on DC analysis, I have table of DC results. So I go ahead and click this particular guy, and I want to, so I can see all the values. And so here we happen to have these. In fact, why don't I go ahead actually and make this one what we have. So I'll double click this guy, and this guy was given as 27 volts, yes? So now I have a 27 volt. Double click this guy, and this was 780. So I'll make this 780 and enter. And double click this guy. This guy was 1.5. So 1.5K. And hit enter. So now I go 1.5K, double click this guy. This was 560, 560, enter, and double click this guy and make this 330, 330 and enter. So now this is the TINA version of our circuit, yes? 27 volt source, first branch has R1, R2, has a 780 ohm resistor, 1500 ohm resistor. Second branch has R3, R4. R3 is 560 ohms, R4 is 330. So now when we do an analysis, our numbers should jive with our calculations unless we blundered in our calculations. So we hit analysis, hit DC analysis, come to table of DC results, boom, and bring this down. And guess what? Do our branch currents match? Do we have 11.84 milliamps for the first branch, second branch? Do we have 30.34 milliamps with the second branch? Do we have 9.24 volts for first resistor? Do we have 776 for the second resistor, 1699, 10.09 voltage source, voltage source? So everything looks like it's jiving there so far, yes?
Yes. So my question is, on the yellow numerical in a box there, like number 1 and number 2.
Yes.
How is that impacting any, or is that just a reference point of some sort?
Let's take a look here. Number
when I
one,
did,
two, yes.
when I tried to follow your exercises,
Mm-hmm.
the placement of those boxes seems to be a bit off from where you've originally. So I just want to know if there's an electrical impact on it,
I would
or
say
as
at this
opposed to
point,
the reference.
yeah, I would say at this point not to worry about those being either similar or different because I didn't place those yellow boxes. They came about. They came about by the program, so that came about by the program. I did not deposit them. So if your yellow boxes, if you have yellow boxes and your yellow boxes are numbered in different places, not to worry about that for now. The bulk of what we're most concerned with in the initial part of our analysis is we've done it on paper and we've built it in TINA and we've double checked our values and they're spot on with our calculations. So that is what I would say for us right now. I will do some further research and find out what the yellow boxes are. I don't know because they don't appear in the multi-sim that we've used in the classroom. This is a new piece of software for me too. I love it because it's free, but I haven't had time to explore all of its nuances yet. So for the time being, I don't, if you have yellow boxes and they are numbered in different places, I would say not to worry about that for now until I do some further research. Most important thing is to look at these numbers. Do they jive with our calculations? And hey, they're spot on.
Yep. Okay, thanks.
Yeah, you're very welcome. I appreciate the question. Did everybody get a chance to see that building the circuit in TINA didn't take much time at all? That changing the values to match our circuit doesn't take any time at all. And so here's the thing. You want to make sure you can do your analysis without having this as a preview. Don't use TINA as a preview for what these numbers ought to be. Try to do your circuit analysis, get some numbers on paper first, and then come back and compare the numbers. Now, once you finish, I would advise you to do this. File, save as, make sure that you're saving to a location where you have your other TINA files. And I'm going to have to go to this PC and I'm going to have to go to on this drive and I'm going to have to go to my TINA folder because that's where my repository is. And as you can see, I have other things on here already. And so this will be a parallel dash series for R because there's 4 resistors in this particular one. And then I'm going to hit save. And you should save each and every one of these with the names that I give you to save them as. If you haven't, not to worry, they're easy to build new ones. But the nice thing about having that repository of saved circuits is I can always click here. I can always, where's my, oh, first of all, I have to close this guy. So cancel. Okay, I've already saved this. I can now open and my resource here, so I can open up any of the ones I've previously built and hit open and kaboom. There it comes up on the screen for me to do with and modify as I please. So in the future, if you happen to have some circuit that looks similar to what we've built before, you can call up a previous design and just modify things and then do a save as. So if, for example, I gave you a 5 resistor circuit, all you have to do is click this wire, hit your delete button. Is that wire gone? Yep. Select this wire. It's selected by virtue of it being red. Hit the delete button. Is that gone? Yes. Select this wire, delete that, select this guy, and let me rotate it this way. Let me put this guy out here, and let me bring in a new resistor and put this down here. The program will automatically number the next resistor in sequence. And now I will go ahead and connect the wires here, there, and there, and there. So now do I have a series? Would I have a series 5R. Okay, that's how easy it is to modify an existing one just by snipping some wires and bringing in a new device. So you don't have to redraw the entire circuit if the new circuit assignment is similar to something we've done before. So this is a suggestion on working smarter, not harder. So I will do a file save as. Boom. And this will become a 5R. It's incomplete, but it is a 5R. So save. So now in my repository, if I hit here and open, I now have a 2R, 2R, 3R, 4R, 5R, and a series parallel or parallel series 4R. And you want to start building your library in this fashion in one folder in your somewhere in your system. So is this helpful for some of our friends that have not finished the series 3R and the series 4R TINA circuits?
Yes.
Okay, all right. I hope that it is. I hope it's informative and helpful all the way around. This is very good. Any questions in general regarding TINA other than Pedro and Christian acquiring borrowing a PC for the use of this exercise? Okay, cool. All right. Now, we have a little more time remaining. Let's go ahead and do a series parallel analysis. So I will stop the share and go back to my .cam. Here we are, .cam, and we will dispense with this. And I have a new piece of paper. Okay. And on my new piece of paper, what I'm going to do is I'll get you something a little cleaner that's doesn't have stuff that's happening in the background, okay? All right, so this new circuit will look like this. What can I torture you, inspire you with now? How about one of these? How about a series parallel? Okay, series parallel. And so here, I'm going to do something a little different. Node A, node B. And I'm going to number these R1, R2, R3, R4. Make this 18 source. While you're copying that down, I'm going to go ahead and do a VIR chart here. 4, 3, R2, R3. Could somebody mute their microphone because we can all hear the noise that's in the background, please?
Mr. Bolito, if you can mute your button.
Thank you. That's very helpful.
Christian, if you can mute your button.
All right, let me give you some ohms to think about. Let's go ahead and make R1 1.8 kilo ohms. Let's make R2 980 ohms. Let's make R3 220 ohms. It's a little hard to read, I apologize. Let me fix that for us. Will be 220 omega. And let's make R4 850 ohms. So that compels us to be very, very careful how we fill in our chart. So our chart will be filled in with R1 1.8 kilo ohms, R2 is 980 ohms, R3 is 220 ohms, and R4 is 850 ohms. Our voltage source is 18 volts. And our circuit polarities are negative, positive. Yeah, get used to looking at things from a variety of different perspectives. All right. So we stated earlier that we have a process for analysis. And that process for analysis is called what class? Circuit reduction. And the how requires us to do what? Redraw the circuits. And then the why is to simplify. So we're going to redraw this particular guy. And as we redraw this, I said you can draw it to the left, right, and anywhere you want. I find it very helpful to draw them immediately below the original circuit, and I keep any identifying landmarks to stay in the same place. So I clearly will retain a point A. I clearly will retain a point B. I clearly will retain my voltage source, negative plate on top. This comes up to here. This guy comes down to here. Now, how do I approach my circuit reduction? How do I approach redrawing this? Before we parted company, I made a suggestion, and that was wherever you see the voltage source, put your eyeball at some point farthest away from the voltage source. So we may choose to put our eyeball from this perspective looking in. And if our eyeball is at this perspective looking in, we see a wire. What do we see on that wire? This end of the wire goes and attaches to node A. What's on this end of the wire? A resistor. And then it attaches to node B. Is there anything else on that wire between A and B other than the one resistor?
Nope.
Nope, not at all. Okay, so there's no series resistor here that I can combine with it, no series resistor here that I can combine with it. What do I do? Who's got a suggestion? Raise their hand. or call your name out.
And you combine it with R2,
Who's offering that suggestion?
Christian.
Christian. Okay, Mr. Cortez, how would we combine it with R2? Do you see a relationship between R1 and R2?
Parallel.
Ah, is everybody in agreement that R1 is in parallel with R2? Are they truly in parallel with each other? What makes them in parallel? Do you remember the definition for parallel? Components are in parallel if and only if the wires on one side of these devices meet at one common node. So do the upper leads meet at node A?
Yes.
Do the lower wires meet at point B?
Yes.
Yes. Therefore, R1 and R2 clearly are in parallel with each other, yes?
Yes.
So I should be able to simplify these two guys into a single equivalent resistance. And let's call that simple equivalent resistance. We'll draw that here. We'll call this REQ1. And that was equal to R1 in parallel with R2. Yes, that's the relationship that gives us REQ1. And then what happens between point A and the source? Nothing other than to copy an original circuit resistor here, R3, and copy this original circuit resistor here, R4. R4 is 850 ohms. This is still 18 volts, and this is still 220 ohms right there.
Those two are
And the
parallel
polarity is, that's an interesting observation. Is R3 in parallel with R4?
Yes.
Again, let's check the definition for parallel. The left-hand lead of R3, is it connected with the left-hand lead of R4 at one common node?
No.
No, because there's a resistor in the way, right?
Yeah.
Is the right-hand lead of R3 and the right-hand lead of R4, are they connected to a common node? No, I've got a voltage source in the way. So although they're drawn in a four-square box and geometrically they are parallel to each other, they are not, however, electronically parallel to each other according to our definition. Are we clear on that?
Yes.
Okay, that's, and again, whatever ideas come to mind, bring them out. Don't be shy, because we learn from these observations. You have an observation, you throw it out there, and if it's right, great. If it's wrong, it's still great, because you're thinking, and that's what I want to have, is the mind is working. So we leave R3 as in its original position, and we leave R4 in its original position, because they don't have a parallel relationship at this point that allows us to do any combination. So this is a good redraw to take us from 4 resistors now down to 3 resistors. So far, so good?
Yes.
We now need to redraw this again. We need to bring this down to a single resistance. We need to bring it down to an R total. So do you see a relationship between these components that we can bring down to an R total?
They're all in series now.
They're all in series. There is only one current path here for the electricity to flow, from the negative through R3, through EQ1, through here, through here. So we should be able to redraw this to become here. This is an 18-volt source, and this will become a single resistance, and this will become R total. Node A is gone, node B is gone. They've disappeared because they were existing between R3 and R1. They're now no longer part of our drawing. Let me say this. You need to calculate the parallel relationship between 1.8K and 980. So hopefully you have done that. You can use product over sum, or you can use reciprocal method. Whichever method you choose is okay, but let's see what you come up with in your calculation. So REQ1 will be your 1800 in parallel with 980. So your keystroke sequence was 1800 reciprocal plus 980 reciprocal equals, and you hit your reciprocal key one more time, and you hit equals one more time. And I'm looking for the first digit of that parallel relationship.
6.
Who gave me the 6?
Andrew.
Andrew gave me the 6. 6 is correct. I'm looking for the second digit, somebody.
Rebecca, 3.
Rebecca, it is a 3 is correct. Who's got the third digit?
4.
4, who gave me that?
Kyle.
Kyle, good. All right. Now I'm looking for the digit after the decimal point. Who's got that?
It's a number 5.
It's a number 5. Very good. Thank you, Pauline. Now I'm looking for the second digit after the decimal point. Somebody give me that.
3.
And that's a 3. And we follow that with an omega. So is everybody okay that this value works out to be 634.53 ohms? Yes? So far, so good. All right. So now do we have enough information to calculate an R total? We simply take this number that's on our calculator and hit plus 220 plus 850. And Mr. Bolito,
Yes.
what is your total, sir?
Let's see.
Do you have that for us yet? Yes or no?
No.
Okay, Mr. Lau, do you have a total for us?
2.05.
Mr. Lau? Pedro, do you have a number for us?
1.7 kilo ohms.
1.7. And what would be the digit after the 7, my friend?
0.
Would be a 0, correct. Kilo ohms. 1.70 kilo ohms. Any questions about that value? We will fill that in here. 1.70 kilo ohms. Very good. All right, this is nice. So what do we do from here? Yes, we want to mark our polarities. This is positive, this is negative, and electrons are flowing this way, like so, like so. So we have a total voltage, we have totals. The only thing left to calculate here is total current. And here we're going to remind ourselves with Ohm's law, V, I, and R. If I am looking for the I simply cover that part with my finger, and I'm going to take V and divide by R. Yes, so the 18 will be divided by the number we have in our calculator. So we will do this. 18 divided by this number, divide by this number. Okay, I am looking for total current. Somebody give me the first digit.
1.
1 is correct. A second digit, somebody?
0.
0 is good. Somebody give me a third digit.
5.
5 is good. How about the second digit after the decimal point?
9.
It is a 9.
Oh, 9.
9.
Wrote it down.
Oh,
I got it. Really? I got a 6. How many other ones get 6? Okay, let's do it this way and show you how that came about. Let's do 18 divided by 1.7 second exponent 3 Oh, I see what happened. All right, let me show you what happens on the calculator. If we do the number that you see rounded here, 18 divide by 1700, same thing, you will end up with a 10.59. What I have here is there's a whole lot more information to our current. Our total ohms. Our total ohms, instead of 1.7 kilo, instead of 1700, actually is up here. It's 1704.5. So it has a bunch of giblets. So what I end up doing on my calculator is I do 18 like you all are doing. I hit divide like you all are doing. But instead of typing in 1700, I have the ability to pop up here and capture the calculation from before, bring it down. So I have all the digits and the giblets after the 1.7 kilo. And now if I hit enter, I end up with a 10.56. So I will keep the 10.56 on here, but I will certainly accept the 10.59 milliamps. So write down 10.59 milliamps, so 10.59 milliamps. But that's why there's a slight difference between your calculator result and mine. And we could be a couple hundredths of a decimal off. We're okay. All right. So does everybody understand how there's a difference between my calculations and yours? Has to do with the ability of this calculator to be able to capture a number from a previous calculation with all of the digits and implement that in a subsequent calculation. Okay. All right, cool. We now have a total current, and I will write down here 10.59 milliamps, okay, just to be consistent with all of you. All right. Well, we still have 8 boxes to fill. So just because we found one current, have we found them all?
No.
No, because the original circuit is not a simple series circuit. However, what do we happen to have in the middle in our drawings? We happen to have a nice series circuit right here. So if we take this information from our most recent redraw and transfer it up here, we know the current leaving the source is 10.59 milliamps. We know the current coming back to the source has to be 10.59 milliamps. And the current going through, down through REQ1 is also 10.59 milliamps. So we have 10.59 flowing throughout the series circuit. Does this 10.59 milliamps happen to flow through any series components in this circuit? It flows through each of these series components because that's in series, that's in series, that's in series. And what do we know is the same in a series circuit is the current. So do you now have 2 currents that we can fill in on our chart?
Yeah, we can put it for I.
Well, we're filling in I, yes. We have 4 squares to fill in, but what are we going to fill in where? Which one of these cells am I going to fill in?
R3 and R4.
R3 and R4.
Oh, R3,
R3 and R4, yes. This is my 10.59 milliamps here, and I have 10.59 milliamps here. I cannot fill in 10.59 for R1 and R2 because R1 and R2
Are different.
they split the current. Because if I take this information from here back up to my original circuit, my 10.59 milliamps that leaves the source does indeed flow through 3. But what happens when it hits node A? It splits. So part of that current proceeds to R1, part of that current splits down to R2. That current through R1 will come down, loop around, go to node B. The current through R2 will come down through R2 into node B, and they recombine to give us the 10.59 milliamps back to the source. So we need to understand that the current through R1 and R2 are not 10.59 because it splits at node A and it recombines at node B. So we cannot fill in this chart with 10.59. That being said, how do I find the rest of these currents?
Current divider formula?
I would go with current divider formula, sure, that would be good. So let's go ahead and reiterate our methods of analysis. So at this point, we would have, for suggestion, CDF, current divider formula, where IRX is equal to RT over RX times IO. So how do I implement current divider formula to find how much current flows into each of these branches? What numbers do I use in this particular formula? So let me give you a for example. If I was looking for IR1 is equal to something over R1 times the total current, what is this numerator going to be? It says RT because this is the general form of the formula. Do I use the RT for the circuit? Do I use the 1.7 k ohms?
No.
No. What should I use in place of RT? What should be the numerator?
634.53.
Precisely. I need to use the RT for only these two guys in parallel. These two guys in parallel came out to be named REQ1, which was the 634.53. So this particular numerator has to be REQ1. And if I go to fill this in now, my IR1 is equal to the 634.53 over 800 times 10.59 milliamps. Those are the numbers that you're going to use. The RT is not the RT for the entire circuit of 1.7 K. The RT is only the RT for these two guys in parallel, which was REQ1, which was 634.53. So I'd like everybody to do this calculation. 634.53 divided by 1800 times 10.59. I will do it as well. So I have that number from before, which I will use. Enter and divide by 1800. Enter and then multiply by that current. And I have a current. So IR1, who would like to call out the first digit, please?
3.
3 is good for the first digit, decimal point. Who would like to call the next digit after the decimal point?
7.
7 is correct. And who would like to call the next digit after the decimal point?
3.
Works out to be a 3. How many people agree with 3?
Yes.
Okay,
Yes, I agree.
milliamps. All right. I'm going to write down 3.73 milliamps. I end up with a 3.72 milliamps. It's okay. We have a slight difference. That's not going to be a problem. So are we in agreement? We have a current here, and I'll write down what you all calculated, 3.73 milliamps. Everybody good with that? Cool. Actually, use a darker color. 3.73 milliamps. All right. So I have a question for you. We have one more current here. How many of you would use this method for IR2? IR2 is the next calculation. So how many of you would take the 1059 and subtract the 7.33 in order to get what's left over for the current for this branch?
I would.
It's going to be
The
the
first time.
Mm-hmm, mm-hmm.
33. I think you just gave us the answer.
No, I didn't give you the answer. 7.3, excuse me. Bleh. No, there. Yes, I did. So I came pretty close to giving the answer. But that's my dyslexia. I see 3.73, but I read it as 7.3. Anyway, I apologize. So how many of you would have taken the 10.59 and subtracted this number to get what's left over, which is something in the 7 milliamp range? You could do that, but I don't recommend that, and here's the reason why. If this was an error, taking the original current and subtracting an error will give you another error. My recommendation is to use current divider again, calculate a new number, and then add the two currents to see if they add up to be the total. Let's go ahead and proceed on this basis. This will become 634.53 over, what do I have here, 980, and then multiply by the 10.59 milliamps. So let's go ahead and generate IR2. Calculate using current divider what this number ought to be. So again, I will do it my way. Enter, divide by 980, and then multiply by this, and I get a current. Pretty close. Pretty close. All right. Who would like to call out the first digit, please?
6.
6 is correct. And who would like to call out the second? It would be an 8. And how about the digit after the 8?
6.
How many people agree with the 6?
I agree.
Okay, 6 milliamps. Okay. And I end up with a 6.84 milliamps. That's okay. We're a few hundredths off. That's not a big deal. I'm happy that you all are in agreement with each other. So we have a branch current here of 6.86 milliamps. And when these two currents come together, the 3.73 milliamps combines with the 6.86 milliamps, does that up to be your 10.59? Exactly. Okay, so your numbers are spot on there and there based on your rounded answers. Cool. Is the last column easy to calculate? Bingo. It's nothing more than voltage is equal to, remember, voltage on our Ohm's law, voltage is equal to I times R. So here's your I, multiply by the R, will get you these voltages. So go ahead and calculate current times ohms, current times ohms, current times ohms, and calculate each of those voltages. And I will check your numbers in a moment. I will calculate the same. Dun, dun, dun. Then enter times O. And enter times 0.8. Cool. All right, plus, enter, plus, enter, and it adds up to 18. Yay, this is good. All right. Okay, I'm calling out for VR1. Mr. Lau, do you have a value for VR1, sir? Wenbin? Yes or no? Pedro, do you have a value for VR1, sir?
6.71 volts.
So you end up with 6.71 volts. How many people agree?
Yes.
I agree.
I agree.
All right, I end up with 6.70, but that's okay. All right, and the voltage for VR2 question goes to Rolando.
Not ready yet. Sorry.
Not ready yet. Okay, question goes to Pedro.
6.72 volts.
6.71 volts. That's where it should round. I end up, again, because I've got super memory, 6.70. If you're off by 100th, that's okay. Should these voltages be the same, my friends?
Yes.
They should be the same, because isn't R1 in parallel with R2? What do you know is the same on parallel branches of a parallel circuit? The voltages have to be the same. My 6.71 volts here has to be the same as the 6.71 volts here, because they're in parallel. So they should appear here as well. How about the VR3? VR3, Pauline, what do you have?
I got 2.33 volts.
2.33 volts. How many people agree?
Yes.
Okay, 2.33 volts. I get 2.32. That's fine. And Rebecca, do you have a VR4, please?
9.00 volts.
How many people agree with 9.00?
I agree.
Yes.
I agree.
I agree.
9.00 volts. Cool. I ended up with an 8.98. All right, we're just
R1, I got 671, and then R2, I got 672.
Yeah, that's okay. Yeah, if we're a hundredth of a decimal place off, that's fine. Yeah, if you learn to use the memories of your calculator, the most correct answer is 6.70 and 6.70, 2.32 and 8.98. But if you're within hundredths of any of these values, the 6.72, I would certainly accept that. Yeah, 2.33 and 9.00 would certainly accept that. Good, this is great. And that didn't take, well, the actual analysis on paper took a bit of time, but the important lesson to learn here is the method. That given a series parallel circuit, we have a process for analysis. That process is called circuit reduction. How do we do this? We use redrawing of circuits. Why? To simplify. And we have simplified this step by step from 4 resistors down to 3 resistors down to 1 resistor. And then we did our analysis here and took our information back up, okay? So the worksheets that you're going to be receiving for the parallel series and the series parallel worksheets will be similar kinds of circuits to these. The voltage sources may be a little different, located in different places. So here was our parallel series, and we may see the voltage source in a different place, but the analysis is still going to be the same method. If you follow these steps and do the VIR chart and look at the different methods of the calculations, then you'll be able to work things out just fine. Building this in Tina is going to be super fast and easy. So without doing the explanation, I'm going to come down here and I'm going to share, and let's see how fast I can pace through this. Dink and share. Okay, now you see my Tina screen. I'm going to do I'm just going to do a file new. That's fine. And I'm going to take this guy, put it over here, and I'm going to rotate this bump twice. So I have the negative side facing up. I'm going to take a resistor and put this over here, rotate this. That's got to be my R1. R1 is going to be over here. put this over here, rotate my R2. It's going to be here. Take this guy, put it over here. That's going to be my R3. Take this, put this guy over here. It's going to be my R4. Okay, now change the ohms on this guy to 1800. So 1800 and enter. And change this guy to 980, 980 and enter. Change this guy to 220, 220 and enter. And change this guy to, what did I say, 850. So 850 and enter. All right, let's connect some wires. This guy will come up to here, go to here. This guy will come up and connect there. This guy will come down to here to connect there. This guy will come down to here, connect there. This guy will come over to here to connect. This guy will come down to here and connect. Okay, looks like it's all connected. Oh, I got to change the voltage source. Voltage source goes to 18 volts. Okay, now do all my values match? Analysis, DC, table of results. Boom. Do I have my 3.72 milliamps that I called out? Do I have the 6.84 milliamps that I called out? Do I have the 10.56 milliamps and 10.56 milliamps that I called out? Do I have 6.70, 6.70, 2.32, and 8.98 that I called out before? Yes. So all of your numbers are within hundredths of these measurements, yes?
Yes, I do
Cool.
have a question.
Please.
So being that there's some hundreds of difference, should we consider the third digit after the decimal instead of the second digit, just to come as close as possible?
No. Just stay doing what you're doing, because showing everybody how to use memory on their individual calculators is a monumental task. And that's fundamentally what it takes is learning how to use the memory of your calculators in order to get your values to be spot on with iCalculate and what the simulator generates as a full DC analysis. Doing what you guys are doing is just fine. You can be within a few hundredths of a decimal place. I'm completely okay with that. If you want to explore, take the time to explore how to use the memory of your calculator, we can take that as a offline, and I'll be happy to discuss that with you all individually. On some calculators, it's easier than others. On some calculators, you already have a memory position 1, 2, 3, 4. Some have 1, 2, 3, 4, 5, 6. Some have a memory A, B, C, D, E, F. 6 memory cells, and they're labeled A in alphabetical order, A through F. So depending upon the memory system of your calculator, you can have calculations that are easily spot on the same as mine as well as what the simulator shows. But I'm not going to require that of everybody because it is, and I've done it before, tried to do it before with like 10 different calculators, how to show 10 different people on 10 different calculators how to use the memory. It's just easier to say, let's just use the rounded numbers and get something that's really close. And since we're within a few hundredths of a decimal place, we're really close. As an instructor, I can't be really close. I have to be anal, and I have to generate numbers that I'm accustomed to with the standard that I've held for myself in the past. And I'm compelled to use memory as often as I can, any way I can. That's why I choose to do this. So that's a long way of answering your question, Pauline, I'm sorry, but did that answer your question?
Yes, thank you.
Okay, yeah. Being a few hundredths off on these numbers right here is perfectly fine. So guess what? I built one. Guess what I'm going to do? File, save as, okay, except now this is a series dash parallel. And this is a 4 resistor, so 4R. So I have a parallel series 4R, and now I have a series parallel 4R, and I'm building up my library of circuits. And you asked an interesting question before. These yellow boxes, they don't appear to be in the sequence of how I've drawn my wires, because I didn't draw my wires in this sequence. So I don't know. I'll have to do some research to see what the yellow boxes mean, but for the time being, they're not significant to us.
Okay.
Okay. All right, my friends, are there any other questions regarding the TINA circuit that I drew really quick for us? Okay, so now that that's saved, that's great. I will stop the share. This is fine. And let's see, this is on the dot cam. So let's go ahead and take us off the dot cam, put this on front cam, and move this out of the way. Were there any other questions that you may have regarding the circuit that we did on paper?
No questions.
Okay, so what I'm going to need to do now, everybody, this is the all view screen, so I can see all of the participants. And as I'm looking at all of the participants, or how can I put my cell phone? Oh, here's my cell phone. I need you all to put on your cameras so I can take a picture of everybody that's on the screen. Mr. Cortez, Rolando, Wenbin doesn't have his camera, so his webcam's not working properly. Christian, do you have one that's working?
Yeah.
There he is. Okay, and so Wenbin is the one who can't. I see Kyle. So this is our official visual roll call. Rebecca, can you lean in more to your camera? There, your happy face. Fantastic. Okay, smile, everybody. Jeez.
Oh my God.
Great. You've been captured on screen.
Already have the camera, but I don't know.
No, okay. All right. So this is great. Excellent session. We've reached the end of our time. I thank you all very, very much for being on the class and for the full experience. It's recorded. This is a really long one. This is the longest one I've recorded. It is a full almost 3 hours. So I don't know how this is going to load or download or even when I'm going to get it from our friends at Zoom. But as soon as I am able to get it and as soon as I'm able to port it in a fashion that's available for you all to review either on my YouTube page or in Canvas, I will alert everybody and let everybody know. So the thing to do between now and next, be on the lookout for these worksheets, something like this guy and something like this guy that we've done for you to analyze. Do finish up the 2R, the 3R and the 4R TINAs, and then I will have more TINA things for us to do that will lead us into more interesting circuit analysis as we move on. Any general questions for me? If they do, send them into Canvas, and I try my best to respond, within 24 business hours, and get back to you with answers to your questions. So don't hesitate to pop anything into Canvas. Okay.
So every new assignment for Tina is going to be in Canvas?
Yes, it will be posted as a JPEG, as a picture, as I've done in the past in Canvas. There will be an upload in Canvas for future TINA exercises, and there will be an upload for these guys as well. So you'll have these guys in the format that I've delivered them before, and you just fill them in. You can take a picture of it and upload the picture of your findings. And then what I would recommend is build your own TINAs, because I'm not going to assign you to do TINAs for every one of these, but build your own TINAs for double checking. So remember, use TINA only for double checking. Don't use TINA for previewing what numbers you're supposed to have. Only if you get stuck. And if you really get stuck, then use TINA. Say, okay, what number am I supposed to get? Because I don't want you to get stuck and stay stuck, okay? All right, so already clear on the best way to use TINA?
Yes.
All right, fantastic. Okay, with that then, have a safe, be sure to maintain your proper social distancing, minimize your outside movements where you can. And I will also have an interesting circuit build thing for us to do that will probably be part of a paper analysis and also part of a TINA analysis, but it will be a circuit build analysis. So we will be able to check these numbers with your multimeters as well. Cool? All right, fantastic. With that, thank you very much, everybody. Have a wonderful, wonderful week.
Thank
And
you.
we will be in touch at Canvas. All right, take care. Bye-bye now.
Thank you.
I'll stop the recording.